Everything you see began in a single, impossible moment. We will explore 25 of the most controversial theories for the universe's origin, ideas that will reshape your understanding of reality itself. You will gain a new perspective on the greatest mystery of all, one that questions the very nature of existence. We will confront proposals where our universe is a simulation, a hologram, or just one bubble in an infinite cosmic foam. Could time itself be an illusion, and did everything truly come from nothing? Which of these daring explanations feels closest to the truth? The most famous answer is also the first great mystery. The Big Bang Theory describes a moment of creation, a point of infinite density and temperature from which everything we know unfurled. It is the bedrock of modern cosmology, supported by powerful evidence. We see the echo of that first fire in the faint, cold glow of cosmic microwave background radiation, a uniform whisper of heat filling all of space. We watch galaxies racing away from us, their light stretched into redder wavelengths, confirming the universe is still expanding outward from that initial event. Yet for all its success, the Big Bang is a door that opens onto deeper, more unsettling questions. It describes the how, but it is utterly silent on the why. What or who triggered that first expansion from a state that defies all known physics? What could possibly exist before time and space themselves began? The theory points back to a singularity, a point where the laws of physics break down, a mathematical placeholder for our profound ignorance. By establishing a definitive beginning, the Big Bang did not settle the debate. It ignited it, creating a vacuum that every other theory on this list attempts to fill. That profound silence left by the Big Bang was not always accepted. For decades, it faced a formidable and elegant rival, a theory that rejected the idea of a beginning entirely. This was the steady-state model, championed by brilliant minds like the astronomer Fred Hoyle. To Hoyle, a universe that simply popped into existence from nothing was philosophically unsatisfying, even absurd. He favored a grander, more eternal vision. In the steady-state universe, there is no creation moment, no starting gun. The cosmos has always existed and will always exist, infinite in both time and space. It expands, yes, but it does not thin out. To maintain a constant, unchanging density across eternity, the theory proposed a breathtaking idea. New matter, a single hydrogen atom here and there, is continuously and spontaneously created in the empty spaces between galaxies. It is a universe in perfect balance, where the overall picture remains the same forever, a cosmic tapestry endlessly weaving itself. Hoyle was so dismissive of the alternative that during a 1949 radio broadcast, he coined the term Big Bang, intending it as a mocking label. The name, of course, stuck, but the theory behind it began to gather undeniable evidence. The decisive blow came in the 1960s with the accidental discovery of the cosmic microwave background, that faint afterglow from the early, hot, dense state of the universe. This was the relic radiation the Big Bang predicted, and the steady state could not naturally explain. Further observations of distant quasars, which showed the universe was dramatically different in its youth, cemented the shift. The data had spoken, yet the philosophical appeal of an eternal, self-renewing cosmos never fully faded. The desire for a universe without a definitive birth or death, one that simply is, continues to whisper in the background of cosmology, a reminder that our search for origins is also a search for meaning. The defeat of the steady-state model seemed to settle the question of a beginning, but the human mind is a restless thing, always seeking patterns and cycles in the chaos. Could the Big Bang be not a unique creation, but merely the latest chapter in an endless, repeating story? This is the compelling promise of the cyclic model, often called the Big Bounce. It proposes a universe without a definitive start or finish, instead trapped in an eternal rhythm of death and rebirth. picture the expansion we see today not as a one-way trip, but as the inhale of a cosmic breath. One day, billions or trillions of years from now, that expansion could slow, halt, and reverse. Gravity would pull every galaxy, star, and particle back together in a cataclysmic collapse known as the Big Crunch. Everything would converge into an unimaginably hot, dense state. But here is the crucial twist. Instead of ending in a meaningless singularity, the universe rebounds. It bounces. That ultra-dense state becomes the seed for a new Big Bang, launching a fresh cycle of expansion, one that erases all traces of the previous universe. It is a phoenix rising from its own ashes over and over again for eternity. This idea elegantly sidesteps the troubling singularity problem of a single beginning, replacing a one-time miracle with a perpetual natural process. Modern physics has given this ancient philosophical concept new form. Some versions, rooted in string theory, imagine our universe as a membrane or brain floating in a higher dimensional space. Collisions between these brains could generate the energy for repeated Big Bangs, like cymbals clashing in the void to start a new symphony. Yet, for all its elegant appeal, the cyclic model faces intense scrutiny. A major challenge is entropy, the universe's tendency toward disorder. If each cycle simply reset everything, entropy would not accumulate. But if information or disorder carried over from one cycle to the next, we should see some imprint, some scar in the fabric of our cosmos. The stunning uniformity of the cosmic microwave background, that fossilized whisper of the early universe, presents another puzzle. For a cyclic model to work, each new universe must be born smooth and uniform, a clean slate. Explaining how a chaotic Big Crunch leads to such a perfectly ordered rebirth is a profound hurdle that theorists are still grappling with, so the debate continues. Is our universe a one-time event, or are we simply living in the current verse of an infinite cosmic poem, unaware of all the stanzas that came before? The eternal rhythm of the cyclic model offers one kind of infinity, but there exists a vision of reality even more expansive and dizzying. This idea shatters the very notion that our universe is the entire story. What if the Big Bang was not a unique creation, but merely a local event, one bubble popping into existence within an endless, frothing sea of other universes? This is the multiverse theory, and it expands the scope of reality beyond all previous imagination. At its heart, it proposes that what we call the cosmos is just one island in an infinite archipelago of cosmic domains, each with its own unique history and, crucially, its own set of physical laws. The constants we take for granted, the strength of gravity, the mass of an electron, the very number of dimensions, could be random variables that change from one universe to the next. In some, atoms might never form. In others, stars could burn out in an instant or live forever. Our universe is not special. It is simply one that, by sheer chance, has the right recipe for us to be here to observe it. This staggering concept emerges from several independent lines of modern physics. The first is cosmic inflation, the theory that our universe underwent a period of hyper-fast expansion just after the Big Bang. Some versions suggest this inflationary process never truly stops. It is a perpetual engine of creation where new pocket universes or bubbles are constantly budding off from the inflating fabric of space-time, each undergoing its own Big Bang. We live in one such bubble, utterly isolated from the others. Then there is the quantum many-worlds interpretation. In this view, every time a quantum particle faces a choice, the universe splits. Did that electron go left or right? The answer is both, creating two branching realities that proceed independently. Over countless quantum decisions, this generates a near-infinite tree of parallel universes, each differing in tiny or monumental ways. Finally, string theory, which seeks to unify all forces, predicts a landscape of possible universes, a cosmic menu with an almost unimaginable number of entries, perhaps 10 to the power of 500. Our universe is just one setting on this vast dial. The controversy surrounding the multiverse is fierce and fundamental. Critics argue it is not science at all, but metaphysics dressed in mathematical clothing. If these other universes are permanently disconnected from our own, causally sealed off, how could we ever test for their existence? Proponents counter that it solves one of cosmology's deepest puzzles, the problem of fine-tuning. The physical constants of our universe appear exquisitely, improbably calibrated for the emergence of life. Change the strength of the nuclear force by a fraction, and stars would not forge carbon. Adjust the cosmological constant slightly, and the universe would either collapse instantly or fly apart too fast for galaxies to form. The odds seem astronomically stacked against us. The multiverse offers a breathtakingly simple answer, a cosmic lottery. With an infinite number of universes playing the game, every possible combination of laws will manifest somewhere. We quite naturally find ourselves in one of the rare universes that can support conscious observers. It is an explanation that replaces cosmic design with unimaginable statistics. Yet it leaves us with a haunting question. Does this infinite cosmic foam grant our existence profound meaning as part of an unthinkably vast tapestry, or does it render our home universe and everything in it utterly insignificant? If the multiverse stretches reality horizontally across infinite possibilities, another theory proposes a radical compression of reality itself. The holographic principle is not a metaphor. It is a serious proposal from the cutting edge of black hole physics and string theory, suggesting our experience of a three-dimensional world may be a magnificent illusion. The idea begins with a paradox. When an object falls into a black hole, it seems to vanish, its information seemingly destroyed forever. This violates a sacred rule of quantum mechanics, which states information can never be truly lost. To resolve this, physicists like Leonard Susskind and Gerard T. Hooft proposed a startling solution. Perhaps the information describing everything that falls into a black hole is not stored within its mysterious interior volume, but is instead perfectly encoded on its two-dimensional surface, the event horizon. It is as if the entire three-dimensional content of the black hole is painted, pixel by pixel, onto its spherical skin. This is the essence of a hologram, where a flat, two-dimensional surface contains all the data needed to reconstruct a full three-dimensional image. Now take this logic and apply it to the entire cosmos. The holographic principle dares to suggest that our entire universe, with all its galaxies, stars, planets, and the very space between them, operates on the same principle. The three-dimensional reality we move through, the solidity of the chair you sit on, the vast depth of the night sky, could be a projection. The true, fundamental reality might be a vast, complex, two-dimensional surface at the extreme boundary of the observable universe. We and everything we know would be akin to shadows on the wall of Plato's cave, intricate projections from a simpler, flatter world of pure information. This leads to a staggering possibility for the origin of everything. If our three-dimensional universe is a projected reality, then the Big Bang might not have been the explosion of a three-dimensional space, but the awakening of a projection from a lower-dimensional template. Perhaps the universe began not as a point of energy in three dimensions, but as a two-dimensional surface etched with an unimaginable density of information. The expansion we see could be that information unfolding, rendering itself into the rich, tangible cosmos we perceive. The quest now is to find evidence. If our reality is a hologram, there should be subtle, granular limits to its resolution, a fundamental pixelation of space-time. Some scientists are searching for this faint noise, this cosmic fuzziness, in the most ancient light we can see, the cosmic microwave background. They are looking for telltale patterns in that microwave whisper, anomalies that could betray the two-dimensional code from which our three-dimensional world is rendered. The implication is profound. It suggests that at the most fundamental level, the universe is not made of stuff but of bits. It is not a place, but a process, an ongoing computation happening on a cosmic screen at the edge of everything we can possibly know. From the idea that reality is a holographic projection, another possibility emerges that is far closer to our own technological experience. The simulation hypothesis proposes that our entire universe, with all its history and complexity, is not a fundamental reality at all, but an artificial construct, a sophisticated computer program. This is not science fiction, but a serious philosophical argument put forward by thinkers like Nick Bostrom. His reasoning follows a chillingly logical chain. First, he assumes it is at least possible for a civilization to advance far enough to create hyper-realistic simulations of conscious beings, perhaps to study their own history. Second, if such a civilization exists, it is likely they would not run just one simulation, but a vast number of them. Now, consider the numbers. If there are countless simulated realities and only one base reality, then the overwhelming statistical probability is that any conscious being, like you or me, is living inside a simulation. We are far more likely to be lines of code than original biological entities. This argument forces a profound existential choice. Either intelligent life almost always goes extinct before reaching such a technological stage, or it chooses never to create such simulations, or we are almost certainly living in one. Many find the third option the most plausible, given our own rapid progress in virtual reality and computing. But if this is a simulation, could we ever detect the evidence? Some physicists suggest looking for the cosmic equivalent of software glitches, subtle shortcuts or inconsistencies in the fabric of reality that a simulating civilization might have used to conserve processing power. Perhaps there are fundamental limits to the small-scale resolution of space, a pixelation of reality at the tiniest levels. Maybe the constants of nature are not fundamental, but simply fixed parameters in the simulation's code. The search for these anomalies is not a joke, it is a frontier of scientific inquiry. The implications, however, ripple far beyond physics. If the simulation hypothesis is true, it redefines everything from free will to the meaning of existence. Are our choices our own, or are they predetermined by an algorithm? Is the beauty of a sunset, the pain of loss, the depth of love, merely an exquisite rendering of data? The theory does not diminish these experiences, but it casts them in a radically new light, transforming the universe from a cosmic accident into a potentially designed artifact, raising questions about the programmer's motives that we may never be able to answer. The simulation hypothesis presents a universe that could be a designed artifact, but another theory from the very edge of physics proposes a creation event of startlingly physical violence. This is the ekpyrotic universe, a specific and elegant form of the cyclic model born from the mathematics of string theory. Its name comes from the ancient Greek word for conflagration, a great fire, and it paints a picture of cosmic birth not from a single point but from a shattering collision. To understand it, you must first envision our reality not as the entirety of existence, but as a three-dimensional membrane or brain floating within a hidden, higher-dimensional space. Think of it as a vast, impossibly thin sheet, a cosmic film upon which all the particles and forces of our universe are confined. Now, imagine another such sheet, another entire universe, hovering parallel to our own in that unseen dimension. In the ekpyrotic scenario, these two brains are drawn together over eons by a faint force, moving slowly, inevitably toward each other. They are not empty. They ripple with energy, strained and warped by their mutual attraction, and then they collide. The impact is not a destructive crash, but a generative one. The immense kinetic energy of the collision is converted into a seething, hot plasma of particles and radiation, flooding our three-dimensional brain. This, according to the theory, is our Big Bang. The universe as we know it begins not with a singularity, but with a resonant clash in the dark. This framework offers a compelling solution to one of the great puzzles of the standard Big Bang, known as the horizon problem. Observations show the cosmic microwave background is uniform to an astonishing degree, meaning distant regions of the early universe must have been in thermal contact, able to exchange energy and even out their temperature. But in the classic model, these regions were moving apart faster than light could have ever connected them. They were causally disconnected, like strangers in separate rooms who somehow decided to wear the exact same outfit. Cosmic inflation solved this by proposing a period of faster-than-light expansion that smoothed everything out from a tiny, connected seed. The ekpyrotic model achieves the same elegant uniformity through the long, slow dance of the approaching brain. As they drew together over an immense span of time, any wrinkles or variations on their surfaces had ample opportunity to stretch out and smooth flat, like pulling tight a rumpled sheet. By the time of the collision, the stage was set perfectly uniform, leading to the even temperature we observe in the afterglow. It is a beautiful piece of theoretical problem-solving, replacing the mechanism of inflation with the physics of colliding worlds. Yet, for all its mathematical beauty, the ekpyrotic universe remains shrouded in profound controversy. Its entire architecture rests upon foundations we cannot yet see or touch, the existence of extra-spatial dimensions and these fundamental brains. While string theory requires such dimensions, no experiment has ever detected even a hint of them. The energy scales involved in brain collisions are so far beyond anything our particle colliders can reach that direct verification seems, for now, a distant dream. Furthermore, the model makes specific predictions about the pattern of gravitational waves, the ripples in space-time from the universe's birth. These waves would have a very different signature than those predicted by inflation. Scientists are actively listening for these primordial whispers with instruments like space-based observatories, hoping the faint tremors in space-time will carry a message about how it all began. Until such evidence arrives, the ekpyrotic universe stands as a magnificent thought experiment, a testament to the human capacity to envision creation as a resonant echo between unseen realities. It asks us to consider that our entire cosmic history might be the aftermath of a long-forgotten impact, a scar healed into a galaxy-filled sky. The violent, generative collision of the ekpyrotic model offers one path to rebirth, but what if the universe's end is not a fiery crunch, but a silent, cold fade into nothingness? Sir Roger Penrose, a Nobel laureate and one of the most brilliant minds in theoretical physics, proposes a cycle of existence born not from collision, but from transformation. His theory is called conformal cyclic cosmology, and it is as elegant as it is radical. Penrose asks us to look not backward to a beginning, but forward to an end, to a future so distant it defies comprehension. In tens of billions of years, the universe will have expanded to an unimaginable degree. All stars will have burned out, all black holes will have evaporated through a process theorized by Stephen Hawking, and all matter will have decayed into its most basic components. What remains is a vast, cold, and nearly empty expanse populated only by massless particles like photons, drifting endlessly through an eternal night. In this state, the universe has no meaningful scale. There is no ruler to measure distance, no clock to tick off time, because all structure, all points of reference have dissolved. This featureless, infinite future, Penrose realized, becomes mathematically identical to the hot, dense, and equally featureless state of the Big Bang. Both are states of pure radiation, devoid of mass and scale. This mathematical equivalence is the key. Through a process called conformal rescaling, a kind of cosmic reset that stretches and smooths the geometry of spacetime, the infinite future of one universe can be seamlessly transformed into the hot, dense beginning of the next. The end becomes the beginning. Penrose calls each full cycle of a universe an eon, and in his vision, our Big Bang was simply the conformal rescaling of the infinite future of a previous eon. It is a cycle without a bounce, without a collision, a silent passing of the baton across a boundary of pure geometry. but a theory this grand needs evidence, and Penrose believes he has found it. He argues that some information might survive this cosmic reset. When supermassive black holes from a previous eon finally evaporated in that eon's far future, they would have released immense bursts of energy in the form of Hawking radiation. Penrose proposes that these titanic explosions could have left faint, circular imprints on the fabric of spacetime itself, imprints that were then carried through the conformal rescaling into our own universe's birth. These imprints, which he calls Hawking points, should appear as subtle, anomalous rings or spots of slightly higher temperature in the cosmic microwave background, the oldest light in our sky. He and his colleagues claim to have identified several such patterns in the CMB data, rings of warmer temperature that they argue cannot be explained by the standard model of cosmology. This claim has ignited a firestorm of debate. Many cosmologists have scrutinized the data and argue that the patterns Penrose identifies are consistent with random statistical fluctuations, the kind of cosmic noise you would expect to find in any complex dataset. They point out that the standard model of inflation already explains the general structure of the CMB with remarkable precision, and these alleged Hawking points are not required. The controversy is a classic clash of scientific paradigms. Is Penrose seeing the profound fingerprints of a previous cosmos, or is he, as critics suggest, finding patterns in the static, much like seeing shapes in the clouds? The search for an answer continues, pushing our instruments and our imaginations to their limits. It forces us to consider a hauntingly beautiful possibility that our universe's spectacular story of galaxies and life is just one chapter in an endless, silent book where every finale is a prelude written in the language of pure light. Penrose's silent cycles of geometry exist at the very frontier of accepted physics, but there is another vision of the cosmos that rejects the foundational pillars of modern cosmology entirely. This is the plasma universe, often called the electric universe, a theory that swaps the dominant role of gravity for the raw power of electromagnetism. Its proponents paint a picture of a cosmos without a beginning, without dark matter, and without black holes, where everything is governed by the behavior of plasma, the fourth state of matter. In this view, the universe is not expanding from a single point, but is eternal and dynamic, shaped by vast, flowing electric currents that stretch across interstellar and intergalactic space. These currents, they argue, twist and pinch the ionized gas of plasma into the familiar structures we see. Galaxies are not held together by the invisible glue of dark matter, but by powerful electromagnetic forces acting along their spiral arms. Stars are not born from the gravitational collapse of gas clouds alone, but are ignited and powered by these cosmic-scale electric currents, functioning more like giant, sustained lightning bolts than thermonuclear furnaces. This framework leads to a wholesale rejection of some of astronomy's most cherished concepts. Black holes are seen as unnecessary mathematical fictions. The intense phenomena at the centers of galaxies are explained as dense plasma focuses or plasmoids discharging immense electrical energy. The redshift of light from distant galaxies, the key evidence for an expanding universe, is reinterpreted not as a Doppler effect from recession, but as a loss of energy as light struggles through intervening plasma over vast distances. For its advocates, this model offers a universe that is more directly understandable, one where the forces we can test and manipulate in our laboratories here on Earth are the very same forces that sculpt the cosmos. Yet, this radical departure comes at a tremendous cost when faced with the mountain of observational evidence. Mainstream cosmologists point to several fatal flaws. First, the theory cannot account for the cosmic microwave background radiation, that uniform sea of microwaves that is the cornerstone of Big Bang cosmology. In the standard model, it is the cooled remnant of the universe's hot, dense youth. In a static, eternal plasma universe, there is no natural explanation for its existence or its near-perfect uniformity. Second, it fails to explain the observed abundances of the lightest elements, hydrogen, helium, and lithium, in the precise ratios that the Big Bang nucleosynthesis model predicts with stunning accuracy. These elements, according to overwhelming evidence, were forged in the first few minutes of a hot, expanding universe, not in an eternal, steady state. Furthermore, the electric universe models alternative explanation for galactic rotation and cluster dynamics, which dismisses dark matter, has not produced quantitative predictions that match the precision and scope of the gravitational models it seeks to replace. While it rightly highlights the often underappreciated role of plasma and electromagnetic phenomena in space, its attempt to construct an entire cosmology upon them stands in stark, unyielding contradiction to some of the most robust and cross-verified datasets in all of science. It remains a provocative outsider, a testament to the human desire for a different kind of cosmos, one where the flicker of a lab spark contains the secret of the stars. Amidst the mathematical collisions and silent cycles of physics, one explanation for existence stands apart, rooted not in equations but in belief. This is the idea of creation by a supreme being, a theory as ancient as human consciousness itself. Across countless cultures and faiths, from the poetic verses of Genesis to the intricate cosmogonies of Hinduism or indigenous traditions, stories have flourished that describe a universe brought into being by a divine will, a purposeful act that imbues the cosmos with meaning and intention. These narratives are not scientific hypotheses in the modern sense, but profound philosophical and theological frameworks that answer the deepest human questions of why we are here and for what purpose. In the contemporary dialogue between science and belief, this ancient idea sparks one of the most enduring and heated controversies. It resurfaces in modern forms, most notably in the concept of intelligent design. Proponents argue that the staggering complexity of life, from the microscopic machinery of a cell to the fine-tuned constants of the universe itself, points not to blind chance but to a guiding intelligence. They highlight the same improbable precision that multiverse theorists use as evidence for infinite chance, but interpret it as evidence for a cosmic designer. This argument from fine-tuning suggests the laws of physics appear exquisitely calibrated for life, as if the universe itself was expecting us. Another philosophical line of reasoning, the Kalam cosmological argument, uses logic to propose a creator. It states simply that everything which begins to exist has a cause. The universe began to exist with the Big Bang, therefore the universe must have a cause. That first cause, the argument concludes, is a transcendent being outside of time and space. This frames the Big Bang not as an uncaused event, but as the very moment of divine creation science has discovered. The controversy lies precisely at the boundary this reasoning tries to cross. Science, by its nature, seeks natural, testable explanations for observable phenomena. It operates within the framework of the universe, asking how things happen. Theistic creation, in its modern philosophical forms, often addresses the question of why, venturing into the realm of the metaphysical, the untestable, and the purposeful. Critics argue that inserting a designer does not explain the designer's origin, effectively pushing the question of origins one step back into mystery. They contend that what we call fine-tuning may yet find a natural explanation within a multiverse or a deeper physical theory we have not yet grasped. The debate, therefore, is less about the facts of cosmic history and more about the limits of human understanding. It is a clash of methodologies, a tension between the search for mechanistic causes and the human longing for ultimate purpose. This enduring conversation reminds us that our quest to understand the universe's origin is not merely a technical puzzle. It is a fundamental part of the human experience, weaving together observation, reason, and the timeless search for meaning in the vast and silent dark. The search for a cosmic creator leads us to a possibility far stranger, one where the universe emerges not from a divine hand, but from the restless churn of absolute emptiness. This is the quantum fluctuation hypothesis, a daring idea that asks if everything we know could be the ultimate statistical fluke. To grasp it, we must first redefine what we mean by nothing. In our daily lives, nothing is an empty box, a silent room, a vacuum devoid of air. But in the quantum realm, the void is never truly still. It is a seething, bubbling foam of potentiality, governed by the uncertainty principle. This fundamental rule states that on the tiniest scales, you cannot precisely know both the energy of a system and the time you measure it. This inherent fuzziness allows for a bizarre phenomenon. Particle-antiparticle pairs can spontaneously wink into existence, borrowing energy from the vacuum itself, only to collide and vanish a moment later, repaying their energy debt. This is not theory, it has been observed indirectly in labs. The quantum vacuum is not a placid nothing, but a simmering sea of virtual particles, a constant dance of creation and annihilation. Now take this microscopic miracle and scale it up to a cosmic, unimaginable degree. The hypothesis proposes that our entire universe could be one such fluctuation, but on a grand, stable scale. In the infinite depths of a primordial void, a quantum fluctuation of staggering proportions could have occurred, borrowing an immense amount of energy to spawn not just a pair of particles, but the seed of spacetime itself. This fluctuation, unlike the fleeting virtual particles, did not immediately collapse. Through a mechanism like cosmic inflation, it was stretched and locked into a stable state, becoming the expanding universe we inhabit. The energy for all the matter and radiation we see would be balanced by the gravitational energy of the expansion, resulting in a universe whose total energy could very well be zero. In this breathtaking view, the cosmos is the ultimate free lunch, something from nothing because the books still balance. Yet, this elegant idea confronts profound challenges. The first is philosophical. The quantum vacuum from which this fluctuation springs is not philosophical nothingness. It is a state defined by quantum fields and the laws of physics that govern them. It is a structured nothing, a something. So the question becomes, did the universe arise from a true void or simply from a pre-existing quantum substrate? The second challenge is one of stability. Most quantum fluctuations are ephemeral. How did this one avoid immediate collapse? This is where ideas like the no-boundary proposal by James Hartle and Stephen Hawking enter the picture. They suggested that if we could run the cosmic film backward to the beginning, we would not find a sharp, singular point. Instead, time itself would become smooth and space-like, like the rounded tip of a shuttlecock. There is no boundary, no edge, no moment of creation that requires an external cause. In this model, the universe simply is, emerging from a quantum state where the distinction between time and space blurs away. It is a self-contained geometric shape requiring no prior conditions, no external spark. The quantum fluctuation hypothesis, especially when paired with such geometric ideas, offers a vision of spontaneous genesis rooted in the known laws of physics, however strangely they behave at the extremes. It replaces the need for a creator with a cosmic roll of the dice on a scale so vast it birthed reality itself, suggesting that in the infinite quiet of the void, something was always destined to happen. The idea of a universe born from quantum chance leads us directly to a profound and unsettling observation about our place within it. This is the anthropic principle, a simple statement with staggering implications that sits at the very heart of the fine-tuning debate. At its core, it is a recognition of a blatant observational bias. We, as conscious observers, can only find ourselves in a universe that has the necessary conditions for our existence. This is the weak anthropic principle. It seems almost trivial, like noting that a fish can only be found in water. If the universe were incompatible with life, we simply would not be here to ponder the question. But this simple logic becomes a powerful lens when we stare at the improbable numbers. The strength of gravity, the mass of the proton, the energy of empty space. each constant seems dialed to a precise value that allows for stars, planets, and carbon-based life. The weak principle says, of course we observe these values, because any other values would lead to a sterile cosmos with no one to do the observing. It reframes fine-tuning from a puzzle demanding a designer to a selection effect. We are not seeing a universe designed for us. We are seeing the only kind of universe we could possibly see. But some thinkers push this logic much further into controversial territory. The strong anthropic principle asserts that the universe must, in some sense, be compelled to have properties that allow for the emergence of conscious life. This is not just a statement about our limited viewpoint, but a claim about the necessity of the cosmos itself. It suggests the laws of physics are not accidental, but are somehow constrained by the future requirement that observers arise. This version often intertwines with ideas of a participatory universe, where consciousness itself plays a role in shaping reality, or with cosmological theories that imply multiple universes. In the vast multiverse landscape, every possible set of physical laws exists somewhere. We inevitably inhabit one of the rare life-permitting universes. Here, the strong anthropic principle and the multiverse work in tandem, one explaining the improbable odds, the other providing the infinite lottery tickets. The controversy surrounding this principle is fierce and deeply philosophical. Critics charge that it is a tautology, a circular argument that explains nothing. Saying the universe is the way it is because we are here to see it feels like a tautological dead end, a fancy way of stating the obvious without providing any causal mechanism. It is accused of being a philosophical cop-out, a way to sidestep the difficult why questions raised by fine-tuning by essentially saying, well, it had to be this way for us. Proponents counter that it is a profound methodological insight, a necessary correction to our intuition. We are not privileged observers at the center of a designed cosmos. We are inevitable products of a statistical filter. The debate ultimately hinges on what we accept as an explanation. Is it enough to identify a necessary condition for our observation? Or must science pursue a deeper causal story for why those conditions exist in the first place? The anthropic principle does not offer a tidy answer, but it forces a brutal honesty about our place in the cosmos, reminding us that our very existence is a filter through which all reality must be viewed. The anthropic filter through which we view reality presents a cosmos improbably suited for us. But what if our entire cosmic home is itself the product of a voracious, all-consuming phenomenon from apparent reality? Black hole cosmology proposes exactly that, a theory as elegant as it is terrifying. It suggests our universe does not simply contain black holes, it may have been born from one. The idea emerges from a striking mathematical symmetry. When a massive star collapses under its own gravity, it compresses into a point of infinite density, a singularity shrouded by an event horizon, a boundary from which nothing, not even light, can escape. Now take the equations that describe this catastrophic inward collapse and reverse the arrow of time. The inward rush becomes an outward explosion. The singularity is no longer an end point but a starting point. The event horizon is no longer a point of no entry, but a point of no return in the opposite direction, marking the boundary of a new, expanding region of space. In this reversed view, the birth of our universe in a Big Bang looks mathematically identical to the death of a star in a black hole. This leads to a breathtaking possibility. Our entire cosmos, with all its hundreds of billions of galaxies, could be the interior of a black hole that formed in some vastly larger, pre-existing universe. We are not outside looking in, we are forever inside, living in the aftermath of a monstrous gravitational collapse that occurred elsewhere. This framework naturally incorporates cosmic inflation. The immense tidal forces and energy densities near the singularity of that parent black hole could have triggered the hyper-fast expansion that smoothed and shaped our early universe. But the theory grows even more fecund, more fertile, with an idea from physicist Lee Smolin known as cosmic natural selection, or the fecund universes theory. Smolin proposed that black holes are not endpoints but cosmic wombs. When a black hole forms in our universe, its crushing singularity does not merely crush matter into oblivion. Instead, it may pinch off and give birth to an entirely new, separate universe, a baby cosmos with its own space-time, expanding into dimensions inaccessible to us. This new universe would inherit its physical constants, like the strength of gravity or the mass of electrons, from the parent, but with slight, random variations like genetic mutations. Here is where a staggering evolutionary logic emerges. Universes that produce more black holes would spawn more offspring universes. Those offspring would inherit the traits, the physical constants, that favor black hole formation. Over countless generations, a cosmic evolutionary tree would grow, selecting for universes that are efficient black hole producers. Our own universe, with its abundant galaxies and stellar graveyards perfect for forging black holes, would not be a random accident. It could be a highly evolved product of this cosmic selection, fine-tuned not for life but for fecundity. The eerie fine-tuning for life we observe might then be a secondary side effect, a fortunate byproduct of constants tuned for stellar collapse and black hole creation. The implications are dizzying. It suggests a form of cosmic heredity where the laws of physics are not fixed and eternal, but evolve across lineages of universes. It offers a potential mechanism for the origin of our own universe without invoking a supernatural creator or an abstract quantum fluctuation from absolute nothingness. Our beginning was not a genesis from void, but a birth from a stellar cataclysm in a forgotten parent cosmos. Yet, for all its conceptual power, black hole cosmology faces immense and perhaps insurmountable hurdles. The most significant is the problem of the singularity. In our current understanding, the singularity inside a black hole is a place where general relativity breaks down, a domain where quantum gravity must take over. We do not yet have a complete theory of quantum gravity to describe what truly happens at that point. The idea that a new universe sprouts there is a compelling speculation, but it remains outside the realm of testable prediction for now. Furthermore, the properties of the universe we see, like its large-scale geometry and uniformity, must align precisely with what would be expected from a black hole interior, a connection that is still hotly debated by cosmologists. Does this mean we are living in a cosmic matryoshka doll, an infinite regression of universes within black holes within larger universes? The theory does not demand infinity, but it opens the door to it, presenting a vision of reality as an ever-branching tree of cosmic fire, where every dark heart contains the seed of a new dawn. The cosmic evolution of black holes suggests a lineage of cause and effect, but what if the very flow of time that defines this sequence is itself a grand illusion? This is the radical proposal of the time-symmetric universe, a theory that dismantles our most fundamental experience of reality. We feel time as a relentless, one-way river, carrying us from a definite past into an uncertain future. But physics, at its deepest level, treats time with a strange indifference. The equations governing the universe work just as well if time runs forward or backward. This mismatch between our experience and the laws of nature is one of physics' great mysteries. Some theorists, like Julian Barber, take this to its logical extreme. He argues that time is not a flowing river at all, but a frozen landscape. In this view, the universe is a single, static, four-dimensional block. Every moment that ever was or will be, from the Big Bang to the heat death of everything, exists simultaneously like frames in a film strip. Our conscious experience of moving from one frame to the next is just that, an experience, a kind of mental projection onto an eternal, unchanging structure. This block universe treats past, present, and future as equally real, a perspective that can feel both liberating and deeply unsettling. A more dynamic but equally strange variation comes from the Wheeler-Feynman absorber theory. It was originally devised to solve a puzzle in electrodynamics, but its implications are cosmic. The theory proposes that for a particle to radiate light, it must interact not only with particles in its future, but also with particles in its past. It suggests a universe where electromagnetic waves travel both forward and backward in time, requiring a kind of cosmic consensus across all of time to allow radiation to happen at all. This hints at a deep symmetry, a universe where the distinction between cause and effect begins to blur. This leads to the mind-bending concept of retrocausality, where future events can influence the past. While not mainstream, such ideas force physicists to confront why we perceive such a strong arrow of time in a seemingly symmetric world. The answer, most believe, lies in entropy, the measure of disorder. The universe began in a state of incredibly low entropy, exquisitely ordered, and has been sliding into higher disorder ever since. This increase gives us the arrow of time, the reason we remember the past but not the future, why an egg scrambles but never unscrambles itself. But this only pushes the mystery further back. Why was the entropy so low at the beginning? The time-symmetric universe offers a wild but elegant solution. Perhaps our universe does not have one beginning in time, but two. Imagine a central point, a moment of maximum order and minimum entropy. From that point, the universe expands not just forward into what we call the future, but also backward into what we perceive as the past. In this two-headed time model, there is no singular creation moment. Instead, there is a symmetrical branching with two arrows of time pointing away from a central, ordered state. From our perspective within one branch, we would experience a big bang and an expansion, with entropy increasing in our forward direction. Beings in the other branch would experience the same, but their past would be our future, and vice versa. This model attempts to solve the low entropy problem by making it a natural midpoint rather than an inexplicable starting line. The universe begins ordered because it expands from a state of order in both temporal directions. It is a beautiful, parsimonious idea, but it remains firmly on the fringe. The primary objection is stark. We have no empirical evidence for a backward-flowing time branch. All our observations, from the expansion of galaxies to the decay of particles, consistently point to a single, unified arrow. Furthermore, our consciousness and memory are processes utterly bound to increasing entropy, making it nearly impossible to conceptualize what existence in the opposite branch would even feel like. Yet, the theory persists as a fascinating thought experiment, a testament to our struggle to reconcile the time-bound nature of our minds with the timeless equations of the cosmos. It asks if our journey from birth to death is a true passage or merely a reading of an already completed book, page by page, in an order we cannot choose. This timeless geometry of the block universe forces us to confront the very nature of the singular point from which everything seems to flow. If the Big Bang was a true singularity, a point of infinite density, then our physics and our logic break down completely. But what if that infamous singularity is not a wall, but a window into a simpler reality? This brings us to the holographic Big Bang, a profound fusion of ideas that reimagines our universe's explosive birth not as a three-dimensional event, but as a two-dimensional projection. We have already seen how the holographic principle suggests our three-dimensional reality might be a shadow cast from information stored on a distant two-dimensional surface. Apply that logic directly to the moment of creation. In this view, the Big Bang singularity is not a point in space, but a boundary in information. The entire hot, dense, early universe, that seething forge of all matter, can be completely described by a hologram on a lower dimensional surface that existed at that moment. Think of it like this: the classic Big Bang picture is like trying to understand a magnificent, detailed sculpture by staring at a single, infinitely dense point of marble. It is impossible. The holographic Big Bang says, do not look at the sculpture from within. Instead, read the two-dimensional blueprint that contains every instruction for carving it. That blueprint is the reality. The singularity is just a misleading artifact of our three-dimensional perspective. Recent theoretical work has painted a vivid picture of this holographic origin. Researchers suggest the primordial cosmos was not a smooth, expanding fireball from the very first instant. Instead, it may have begun as a chaotic, hot hologram, a turbulent and information-rich two-dimensional surface. In this state, the familiar concepts of space and time were not yet stable. They were emergent properties fluctuating wildly. Then, as this holographic system cooled and evolved, it underwent a phase transition. It crystallized, just as water freezing into ice creates a rigid, structured solid from a fluid. This chaotic hologram crystallized into the stable, three-dimensional space-time we inhabit. The Big Bang in this telling is not an explosion in space, but the moment of crystallization from a lower dimensional state. This approach offers a breathtaking solution to the singularity problem that plagues standard cosmology. In Einstein's equations, the singularity is where the math fails, a place where density and temperature become infinite and our understanding ends. But in the holographic description, that point is replaced by a well-behaved boundary, a surface where the equations remain finite and sensible. The mind-bending infinities are tamed by translating the problem into a language without them, the language of quantum information on a surface. The promise is immense, a potential bridge between the quantum world and gravity, a theory of everything born from the first moment. Yet, for all its elegance, the holographic Big Bang exists primarily in the realm of sophisticated mathematics and supercomputer simulations. Testing it against the real universe is a monumental challenge. The primary hurdle is computational. To make a precise prediction about what signatures this holographic crystallization would leave in, say, the cosmic microwave background, physicists must solve extraordinarily complex quantum systems on a computer. These are calculations of such staggering difficulty that they push the limits of our most powerful processors. It is like trying to predict the exact pattern of a snowflake by simulating the quantum state of every water molecule in a cloud. We are not there yet. Furthermore, the model must not only reproduce the successes of the standard Big Bang and inflation, it must also predict something new, a subtle twist in the data that no other theory can explain. Scientists are searching for these telltale signs, perhaps a specific pattern of gravitational waves or a unique fingerprint in the distribution of galaxies across the sky. Until such a prediction is made and confirmed, the holographic Big Bang remains a magnificent and promising sketch, a blueprint for a new origin story written in the language of information, waiting for the universe itself to provide the verification. The holographic origin suggests reality is a projection, but what if space and time are not the stage itself, but merely actors that emerged from the wings? This is the startling proposition of the emergent universe theory. It argues that the very fabric of space-time, the arena in which all cosmic events play out, is not fundamental. Instead, it is a collective illusion, a property that arises from something far more basic, much like the concept of temperature. Temperature is not a thing you can hold. You cannot find a temperature particle. It emerges from the frantic collective motion of countless molecules. In the same way, theorists propose that the smooth, continuous geometry of space and the relentless flow of time might emerge from the interactions of countless fundamental building blocks, perhaps quantum bits of information or a web of quantum entanglement. This flips our entire understanding of the cosmos on its head. The question is no longer what happened in space and time at the beginning, but how space and time themselves came to be. One of the most compelling frameworks for this idea is called quantum gravity. Picture the very early universe not as a tiny, hot, dense ball, but as a chaotic, buzzing network of quantum connections, like a hyperactive beehive with no sense of up or down, here or there. In this primordial state, there is no recognizable space, no distance, no before or after. There are only nodes and links, pure relationships humming with potential. Then, as this network cools, a phase transition occurs, akin to water freezing into ice. The random, tangled connections begin to align and lock into a stable, orderly pattern. From this crystallization, the familiar properties of our three-dimensional space and one-directional time spontaneously manifest. Distances become defined by the number of links between nodes. Causality, the chain of cause and effect, emerges from the flow of information across the network. In this view, the Big Bang is not an explosion in a pre-existing void. It is the moment geometry itself froze into shape. This radically changes the origin story we must tell. We are not searching for a spark that ignited an expansion within space-time. We are trying to understand how space-time condensed, like dew on a window pane, from a formless, pre-geometric fog of quantum relationships. The singularity of classical physics vanishes, replaced by a transition between two states of organization. The profound implication is that at the deepest level, reality might be purely relational, built not from stuff located somewhere, but from the information shared between things. It suggests that what we perceive as the vast, empty stage of the cosmos is actually a dense, dynamic computation, a cosmic network rendering its own geometry in real time. The quest now is to find observational clues that our smooth space-time has a granular, quantum graphite structure if you could probe at a small enough scale. Some scientists look for subtle delays in the arrival times of very high energy gamma rays from distant cosmic explosions, hoping to catch space-time itself pixelating at the tiniest levels. The emergent universe does not just offer a new beginning, it redefines what beginning even means, proposing that the stage of reality assembled itself just in time for the cosmic drama to begin. Emergence paints a dynamic origin for space and time, yet a small coterie of thinkers argues we have profoundly misinterpreted the cosmos entirely. They champion a vision of a static universe, an eternal and unchanging cosmos that never expanded from a singular point. This is not a new idea. It was the dominant view before Edwin Hubble's revolutionary observations in the 1920s. Hubble famously found that the light from distant galaxies was stretched, shifted toward the red end of the spectrum, and that this redshift increased with distance. The standard interpretation is the Doppler effect, the same phenomenon that lowers the pitch of a receding siren's wail. Applied to galaxies, it means they are all rushing away from us and from each other in a universal expansion that traces back to the Big Bang. But what if that interpretation is wrong? Proponents of a static universe propose alternative mechanisms for that pervasive redshift. The most famous is the tired light hypothesis. It suggests that light, over its immense cosmic journey, gradually loses energy. This energy loss would cause its wavelength to stretch, creating the redshift we observe without the galaxies themselves needing to move. The mechanism for this energy loss is the great weakness of the idea. Could it be due to collisions with sparse intergalactic dust or a subtle interaction with the fabric of space itself? No proposed physical process for tired light has ever been found that does not also distort the images of distant objects in ways we simply do not see. Another proposal points to gravity. In Einstein's theory, light climbing out of a deep gravitational well loses energy and redshifts. Could the collective gravity of the universe's structure imprint a redshift that mimics expansion? Detailed calculations, however, show this gravitational redshift would not produce the precise, linear relationship between redshift and distance that Hubble discovered and that has been confirmed with exquisite precision. The static model's appeal is deeply philosophical, offering a cosmos without a beginning or end, a stable, infinite stage. Some modern variations even attempt to incorporate the cosmic microwave background, suggesting it could be the thermal radiation from a halo of hot gas surrounding our galaxy or the scattered light from countless ancient stars. But here, the theory collides catastrophically with the evidence. The CMB is not a local glow. It is spectacularly uniform in every direction, a perfect thermal bath that permeates all of space. A local origin cannot explain this isotropy. Furthermore, the CMB has a specific blackbody spectrum, a fingerprint that matches exactly what you would expect from the cooled remnant of a hot, dense early universe. The static model cannot naturally produce this perfect pattern. The evidence continues to mount. The observed abundances of light elements, hydrogen, helium, and lithium, match the predictions of Big Bang nucleosynthesis to a stunning degree. These elements were forged in the first few minutes of a hot, expanding cosmos, not in an eternal, steady state. Then there are the supernova. Observations of distant exploding stars not only confirm the expansion, they show it is accelerating, a discovery that requires dark energy in the standard model. In a static universe, the brightness of these standard candles would fade in a predictable way with distance alone. But the data reveals they are dimmer than that, exactly as if space itself had stretched more than expected during the light's journey. Faced with this overwhelming, multi-pronged evidence from independent cosmic probes, the static universe theory has been relegated to the farthest fringe of cosmology. Yet it persists. Its endurance speaks to a powerful human instinct, a desire for a cosmos that is permanent and knowable, a fixed backdrop against which our stories unfold. It stands as a stark reminder that in science, even the most elegant and comforting ideas must ultimately bow to the relentless testimony of the data. The overwhelming evidence for an expanding cosmos seems to demand a dynamic history, but what if that entire history and the space it unfolds within is merely a shadow of a deeper, timeless truth? This is the mathematical universe hypothesis proposed by physicist Max Tegmark, and it pushes the idea of cosmic origins to its most radical, abstract limit. Tegmark's proposal is a form of extreme Platonism. The ancient philosopher Plato suggested that the physical world we see is just an imperfect reflection of perfect, eternal forms or ideas. Tegmark updates this for modern physics, arguing that our physical reality is not merely described by mathematics, it is a mathematical structure. Think of it this way. We use the mathematical construct of a sphere to describe a planet, but we understand the planet is a physical object and the sphere is just a model. Tegmark flips this. In his view, the planet is the sphere. More precisely, every particle, every force field, every ripple in space-time is not a thing that mathematics approximates. It is a specific piece of an abstract, self-contained mathematical object. The universe exists because that mathematical structure exists in the same timeless, placeless sense that the number pi exists. It does not sit somewhere, it just is. This leads to a staggering conclusion about origins. The universe did not begin in a fiery explosion. The Big Bang is simply a feature within the mathematical structure, a point from which one particular solution to the equations unfolds. There is no creation moment because the structure itself is eternal and acausal. It was not caused, it simply is, residing in what we might call a Platonic realm of all possible mathematical structures. Our reality is one page in an infinite, timeless book of mathematical truths. The controversy this ignites is profound and philosophical. To supporters, this is the ultimate endpoint of the scientific quest, the recognition that at the bedrock of reality we find not stuff but abstract relationships and logic. It elegantly dissolves the nagging question of what caused the first cause, because in a timeless mathematical landscape, causation is just another relationship within the structure, not something that applies to the structure itself. The universe is not a caused thing, it is a true statement. Critics, however, see this as a philosophical sleight of hand, a retreat from physical explanation into metaphysics. They argue it replaces the mystery of a physical beginning with the mystery of why this particular mathematical structure manifests as our experienced reality. Furthermore, it raises the hard problem of consciousness with new urgency. If the universe is purely mathematical, what are we? Our sensations of color, sound, love, and pain seem utterly alien to the cold, formal world of equations. Is consciousness itself a mathematical pattern, a specific, complex computation running on the wetware of our brains within the grand structure? If so, does that make our inner lives any less real, or does it grant mathematics a shocking, experiential depth we never attributed to it? The theory's greatest challenge, however, is testability. How could we possibly prove we live in a mathematical structure rather than a physical one that mathematics describes? Tegmark suggests that if the hypothesis is true, our universe should be maximally mathematically elegant. We should eventually find a final, simple, beautiful set of equations from which everything flows with no arbitrary, tunable constants. The search for that ultimate theory of everything becomes, in this light, the search for our own cosmic address in the library of mathematical existence. Until then, the mathematical universe hypothesis remains the most austere and mind-bending origin story of all, proposing that we are not beings in a universe, but rather, we are fleeting awareness within an eternal, unchanging truth, reading itself into existence one conscious moment at a time. If our reality is a simulation, where would its seams show? The search for evidence is not science fiction, it is a frontier of physics. Scientists propose we look for the cosmic equivalent of rounding errors in the code. One place to search is in the behavior of the most energetic particles in the universe, cosmic rays. These rays, protons and atomic nuclei hurtling through space at nearly the speed of light, should have a theoretical maximum energy, a cutoff point imposed by their interactions with the cosmic microwave background over vast distances. This is known as the GZK limit. Some researchers suggest that if the universe is a simulation with a finite resolution, a fundamental pixel size, we might see anomalies right at this limit. Cosmic rays with energies precisely at the cutoff might appear or behave in statistically odd ways, as if the simulation is simplifying calculations to save processing power on the most extreme events. Another signature could be a directional bias, a faint preference for these particles to arrive from certain coordinates in the sky, hinting at an underlying grid, a lattice structure to simulated space itself. Beyond particles, we could look at the fabric of reality on the tiniest scales. If space-time is rendered, there should be a limit to how finely it can be divided, a digital pixelation. Experiments searching for quantum gravity effects are, in a sense, also probing for this. Does space become grainy at the Planck scale, 10 to the negative 35 meters? Some models of a simulated universe predict just that, a fundamental fuzziness that would subtly alter how the most energetic light from gamma-ray bursts travels across the cosmos. Even the laws of physics themselves could contain clues. Are there mathematical constants that seem arbitrarily chosen, numbers that work but lack a deeper, elegant derivation? These could be the fixed parameters in the simulation source code, chosen for computational convenience rather than fundamental necessity. The very fact that our universe is so exquisitely mathematically describable could be seen as a hint that it is, at its heart, a mathematical construct. This line of thinking offers a chillingly elegant solution to the Fermi paradox, the profound question of why we see no evidence of other galactic civilizations. If a civilization advances far enough to create realistic simulations, that might become its primary existential activity, a pursuit far more compelling and safer than physical interstellar travel. Such a civilization might retreat entirely into a simulated multiverse of its own creation, or it might be running countless ancestor simulations for research or entertainment. In this scenario, the great silence in the galaxy is not because civilizations destroy themselves, but because they graduate, they become programmers, not explorers, leaving the physical universe quiet and empty. The implications of this possibility ripple far beyond physics into the core of our existence. If we are in a simulation, it forces brutal ethical questions. What are the responsibilities of the simulators? Are we conscious beings with moral worth, or are we sophisticated non-player characters in a game we cannot perceive? If we suffer, does that matter to them? The theory could be used to justify nihilism, the idea that nothing is real and therefore nothing matters. Yet it could also inspire a kind of profound curiosity. Our quest for knowledge becomes an attempt to reverse engineer the simulation, to understand the rules of the game and perhaps even communicate with the architects. This leads to the final recursive twist. If we are likely in a simulation, and if our technology continues to advance, we will eventually reach the threshold where we can create our own hyper-realistic simulations containing conscious beings. At that moment, we would become the simulators, completing a chain of realities that could stretch infinitely backward and forward. Would creating such a simulation be an act of profound creation or unspeakable ethical transgression? The simulation hypothesis does not offer comforting answers, but it reframes the oldest questions in a dazzling new light, transforming our universe from a cold accident into a potentially authored artifact, and our lives into the most mysterious story ever coded. The simulation hypothesis leaves us questioning the very fabric of our reality, but it is not the only idea that stretches science to its breaking point. The multiverse theory, with its infinite cosmic islands, faces a relentless and fundamental criticism. If these other universes are forever beyond our reach, sealed off by the very laws of physics, can we ever truly call this a scientific theory? Or has it crossed the line into untestable metaphysics? This is the central battleground for the multiverse, and scientists are not conceding defeat. They are on a frontier hunt for indirect, ghostly evidence that our cosmos is not alone. One of the most promising searches looks for scars on the oldest map we possess. If our universe is one bubble in a frothing cosmic foam, it is possible, even likely, that other bubbles have bumped into ours during the chaotic period of inflation. Such a collision would have sent shockwaves rippling through the structure of our infant cosmos, leaving a distinct circular imprint on the cosmic microwave background. Imagine throwing a stone into a perfectly still pond, the concentric rings spreading outward. A bubble collision would be like that, but frozen into the fabric of space itself at the moment of creation. Teams of cosmologists have scoured the detailed maps of the CMB from satellites like Planck, searching for these telltale circular patterns of slightly warmer or cooler temperature. A few candidate signals have sparked excitement, but so far none have held up to rigorous statistical scrutiny. The search continues, a meticulous effort to find a fingerprint from a neighboring reality. Another avenue listens for echoes from before time. Some multiverse models, particularly those involving a cyclic universe or a brain collision, predict a specific background of primordial gravitational waves. These are not the waves from merging black holes we detect today, but much older ripples generated in the first instance of our universe's birth, or even from events in a cosmos that preceded our own. These waves would imprint a faint, swirly pattern on the polarization of the CMB light, a signature known as B modes. Detecting this specific pattern would be a monumental discovery, potentially a window into the pre-Big Bang multiverse. Experiments are underway at the South Pole and in space, their instruments chilled to near absolute zero, listening for this whisper from beyond our bubble. Beyond direct observation, some theorists use the anthropic principle as a tool for statistical prediction. If we live in a multiverse where physical constants vary randomly, then the values we measure in our universe should not be the most likely values overall, but rather the most likely values that allow for observers. This leads to a form of reasoning called anthropic prediction. For example, in a landscape of possible universes, the cosmological constant, the energy of empty space, could have any value. In most universes, it would be enormous, causing instant collapse or runaway expansion. We, of course, find ourselves in a universe where it is extraordinarily small, allowing for galaxies and life. By calculating the statistical distribution of observers across the multiverse landscape, scientists can ask, given that we exist, what value of the cosmological constant should we expect to see? Remarkably, some simple anthropic calculations predict a value roughly in the ballpark of what we observe. This is not proof, but it is a form of consistency check, showing that our observed reality is not an outrageous statistical outlier within the multiverse framework. Yet, for all these ingenious efforts, the core criticism remains fierce and philosophical. Prominent physicists like Paul Steinhardt have argued that a theory that posits an infinite number of unobservable entities is not science but a philosophical surrender. It explains everything and therefore predicts nothing specific about our own universe. If any observation can be explained away by saying it happens in our particular bubble, has the theory lost its power to be falsified? This strikes at the heart of the scientific method. Proponents counter that the multiverse is not an assumption, but a natural consequence of our best physical theories like inflation and string theory. To ignore it would be to ignore the logical implications of our own mathematics. They see it as the necessary, if unsettling, extension of cosmology, the only coherent way to explain the bizarre fine-tuning we witness without invoking a designer. The debate is a profound rift in how we define the limits of science. Is the multiverse a bold prediction of cutting-edge physics, or is it a speculative dead end, a cosmic castle built in the air of untestable mathematics? The answer may depend on whether those frozen rings in the microwave sky or the faint swirl in ancient light ever reveal themselves. Until then, we are left straddling two worlds, one where our universe is a lonely accident, and another where it is just one page in an infinite, unreadable book. The relentless increase of entropy presents a brutal challenge to any eternal cycle of universes. If disorder only grows, each new cycle would begin with more chaos than the last, like a photocopy of a photocopy, each one fainter and more degraded. Over infinite repetitions, this would lead to a cosmic heat death, a featureless, high-entropy soup from which no new structure could ever emerge. A true cyclic model cannot simply ignore the second law of thermodynamics. It must find a way to reset the cosmic clock, to smooth the canvas clean for each new painting. Modern theorists like Paul Steinhardt and Neil Turok have proposed a breathtaking mechanism within their ekpyrotic framework that attempts to do just that. In their vision, our three-dimensional universe is a brain, and the Big Bang is the result of a collision with a parallel brain. This collision generates the heat and matter we see, but crucially, it also provides a pathway to erase the accumulated entropy of the previous cycle. Imagine the entropy, the disorder, of the old universe not as something destroyed, but as something stretched and diluted. When the brains collide and rebound, the three-dimensional space we inhabit is violently stretched and smooth. The entropy from the previous cycle could be spread so thinly across the newly expanding volume that, from our perspective within the new universe, the starting point appears exquisitely ordered and low entropy. It is as if you took a single drop of black ink, the entropy of the old cosmos, and released it into a freshly filled, clear ocean. The ink is still there, but its concentration is so vanishingly small that the entire ocean appears pristine. Furthermore, the long, slow approach of the brains before the collision naturally irons out any wrinkles, creating the perfectly smooth and uniform starting conditions we observe in the cosmic microwave background. This process, in theory, resets the entropy counter for the new cycle, allowing for galaxies, stars, and life to form all over again. But does this truly solve the problem, or has it merely been relocated? Critics argue that the entropy has not vanished. It has just been transferred or hidden in the extra-dimensional bulk, the space between the brains, the total entropy of the entire higher dimensional system might still be increasing, even if our local three-dimensional bubble gets a fresh start each time. We are not witnessing a violation of the second law, but a clever accounting trick where our universe only sees the clean balance sheet, while the cosmic ledger in the higher dimensions grows ever more disordered. This shifts the ultimate heat-death from our universe to the multiverse at large. The question then becomes whether a theory that solves a problem by moving it to an arena we can never observe is a legitimate scientific solution or a philosophical workaround. The quest continues, a search for a cyclic process that is truly, fundamentally reversible, or for evidence within our own cosmos that points to a previous cycle's diluted entropy, a ghostly signature of an ocean that once contained a single, ancient drop of ink. The ultimate test of any cosmic theory is not its elegance, but its ability to predict what we actually see in the sky. For the plasma universe, this confrontation with observational data is where its radical vision faces its most severe challenges. Take the cosmic microwave background, that uniform sea of microwaves that permeates all of space. The standard Big Bang model predicted its existence and its precise character, a perfect blackbody spectrum. This is the thermal fingerprint of a hot, dense, expanding origin, and satellite measurements have confirmed its blackbody nature with astonishing precision. The plasma universe, proposing an eternal and static cosmos, struggles to provide a natural source for this radiation. Suggestions that it could be the scattered light of countless ancient stars or thermal emission from interstellar dust fail catastrophically to produce the perfect, smooth, all-pervading blackbody spectrum we observe. Any local origin would create a patchy, uneven glow, not the magnificent uniformity that blankets the entire sky. Then there is the primordial recipe of the cosmos. Within the first few minutes of the hot Big Bang, nuclear fusion forged the lightest elements, hydrogen, helium, and traces of lithium, in very specific proportions. The predicted abundances, about 75% hydrogen and 25% helium by mass, match the observed ratios in the oldest stars and in distant, pristine gas clouds with breathtaking accuracy. This is a cornerstone prediction of the standard model, confirmed repeatedly. The plasma universe, lacking that initial hot, dense phase, offers no coherent, quantitative mechanism to explain why these elements exist in precisely these universal ratios. In a static, eternal cosmos, element production would be an ongoing, localized process in stars, leading to a chaotic mix of abundances, not the clean, foundational signature we see everywhere we look. The discrepancies extend to our own celestial backyard. Standard solar models, which describe the Sun as a gravitationally confined thermonuclear furnace, make precise predictions about the neutrinos it emits, tiny ghostly particles that stream out from its core. Decades of neutrino detectors have now confirmed these predictions, capturing the exact flavors and numbers expected from nuclear fusion. Plasma cosmology's alternative view of stars as electrically powered entities makes very different predictions about solar structure and energy output, predictions that do not align with the neutrino data or with detailed heliosismology, the study of the Sun's internal vibrations, which acts like a sonogram of its interior. The Sun's heartbeat, it turns out, matches the rhythm of a nuclear heart. This stark divergence is a powerful case study in the scientific method. A theory gains credibility not through philosophical appeal, but through its predictive power, its ability to make bold, testable claims that are then verified by observation. The plasma universe makes a suite of predictions about galactic rotation without dark matter, about the nature of redshifts, and about stellar mechanics that consistently fail to match the precision and scope of the data explained by mainstream cosmology. It is not merely that the standard model has evidence, it is that the alternative model's specific predictions are repeatedly contradicted by it. This relentless empirical pressure is what ultimately shapes our understanding of reality, guiding us away from compelling stories and toward descriptions that, however strange, consistently mirror the universe as it truly is. This exquisite calibration of the cosmos presents a dilemma that cannot be solved by equations alone. The fine-tuning of the universe's constants is so precise it feels intentional. The cosmological constant, which governs the energy of empty space and the acceleration of the universe's expansion, is fine-tuned to an almost absurd degree. If it was slightly larger, even by 1 part in 10 to the 120, the universe would have blown itself apart before stars could ever form. If it was slightly smaller, gravity would have pulled everything back into a catastrophic collapse almost immediately. Similarly, the strength of gravity itself, the force that sculpts galaxies and binds planets to their suns, sits within a razor-thin window. Strengthen it just a bit, and stars would burn through their fuel in millions of years instead of billions, leaving no time for planets to cool and life to evolve. Weaken it, and matter would never clump together into stars at all. This pattern repeats for the nuclear forces, the mass of fundamental particles, and the initial conditions of the Big Bang itself. The universe appears built on a knife edge of possibility, a cosmic house of cards where changing a single card causes the entire structure to collapse into sterility. This observation, known as the fine-tuning problem, is one of the most profound in all of science because it demands an explanation. Why is the universe so hospitable to us? Two grand, opposing answers have emerged, each with monumental implications. The first is the multiverse, a naturalistic explanation we have explored. If an infinite or near infinite number of universes exist, each with randomly dialed constants, then it is no surprise that at least one, by sheer chance, has the right combination for life. We, of course, find ourselves in that one. In this view, fine-tuning is not evidence of design, but a statistical inevitability, a cosmic version of a lottery winner marveling at their own luck without considering the millions of losing tickets. The second answer is design, or the theistic interpretation. Here, the exquisite precision is seen not as a lucky draw, but as the signature of a cosmic architect. The constants are not random, they are chosen, set with intention to create a universe capable of hosting conscious, moral agents. This argument resonates because it speaks to a deep human intuition about purpose and meaning in the cosmos. It suggests the universe is not a cold, accidental void, but a crafted arena with a goal. Between these two giants stands a third, more austere philosophical position, sometimes called the brute fact. This stance argues that asking why the constants have these values is a meaningless question. They simply are. The universe exists with these properties, and there is no deeper reason, no cause, no designer, and no need for an infinity of other worlds. The constants are foundational, and we must accept them as the starting axioms of reality, much like a mathematician accepts the properties of numbers without demanding to know why 2 plus 2 equals 4. This perspective is philosophically clean but emotionally unsatisfying, as it asks us to accept the most staggering coincidence in existence as just a given. Underlying this entire debate is a more fundamental question: is fine-tuning even a real problem, or is it the ultimate example of selection bias? This is the hard edge of the anthropic principle. We can only observe a universe that allows for observers. It is logically impossible for us to find ourselves in a universe where the constants forbid our existence. So, while the odds of this specific universe seem astronomically small, the probability of us observing it, given that we are here to observe, is exactly 100%. From this angle, fine-tuning is not a puzzle to be solved, but a condition of our own existence that requires no further explanation. It is the cosmic equivalent of a fisherman being surprised that all the fish he catches are from the water and never from the desert. This makes the fine-tuning debate the ultimate intellectual battleground, a place where empirical science, speculative cosmology, and fundamental philosophy collide. It is not a fight over data, but over interpretation, over the limits of explanation, and over what kind of story we tell about our place in the cosmos. Do we live in a lonely, purposeful creation, a single page of scripture in an otherwise silent book? Or are we one accidental paragraph in an infinite, unread library of random text? Or perhaps we are simply here, and the question itself is a mirage created by our own limited perspective. The answer you find most compelling may say less about the universe and more about what you believe a satisfying explanation truly is. The stark choice between a cosmic designer and an infinite multiverse seems to leave no room for a third option, but deep within the mathematics of space and time, a different kind of answer is being forged. This is loop quantum cosmology, a leading contender in the quest to quantize gravity and rewrite the story of the Big Bang itself. It emerges from a broader theory called loop quantum gravity, which approaches the problem of unifying general relativity and quantum mechanics from a radically different angle than string theory. Instead of proposing tiny, vibrating strings in extra dimensions, loop quantum gravity suggests that space itself is not a smooth, continuous backdrop. It is woven from a fabric of tiny, indivisible loops, a network of intersecting threads of gravitational field. Space has a structure, a finest possible weave, much like a piece of cloth is made of individual threads. You cannot have half a thread, you cannot have a piece of space smaller than this fundamental quantum of area. This granularity of space is the key that unlocks a new origin story. In Einstein's equations, the Big Bang is a singularity, a point where density and curvature become infinite because the math breaks down. But in loop quantum cosmology, you cannot compress space infinitely. As you rewind time toward the beginning, gravity becomes repulsive at these extreme densities due to quantum geometry effects. The universe reaches a maximum possible density, a cosmic traffic jam, and then rebounds. The Big Bang is replaced by a big bounce. Our expanding universe did not emerge from a point of infinite mystery, but from the collapse of a previous cosmic phase. We are living in the aftermath of a great quantum rebound. This paints a breathtaking picture of a pre-Big Bang universe, a contracting cosmos that reached a state of incredible but finite density before quantum gravity pushed back, initiating the expansion we see today. That prior universe could have been vast and old, perhaps even similar to our own, collapsing under its own gravity until quantum effects took over. The transition through the bounce is not a violent smash, but a smooth quantum transition, a cosmic handoff where the laws of physics remain well behaved. One of the theory's great strengths is that it naturally eliminates the troubling singularity, replacing the wall of infinities with a quantum bridge to a possible past. It provides a clear, physical mechanism for a cyclic universe without needing colliding branes or conformal rescalings, using the intrinsic quantum properties of space itself. Yet, for all its conceptual elegance, loop quantum cosmology faces a monumental challenge, the same one that haunts all quantum gravity theories, making testable predictions that distinguish it from the standard model of inflation. The theory can describe the universe's evolution through and before the bounce, but the intense quantum effects during that transition tend to smear out any detailed information from the previous cycle. It is as if the universe passes through a cosmic blender, emerging smooth and uniform on the other side, which is good because we observe a smooth universe, but bad because it erases potential fingerprints of what came before. Scientists are working tirelessly to find subtle signatures that might survive. One possibility is that the quantum bounce could imprint a specific twist or pattern on the primordial gravitational waves, the oldest ripples in spacetime. Another is that the granular nature of space might leave a faint statistical mark on the cosmic microwave background, a preferred direction or a break from perfect uniformity at the very largest scales. Detecting such signals would be a smoking gun, but it requires exquisitely precise measurements that push our technology to its absolute limit. For now, loop quantum cosmology stands as a powerful and promising sketch, a vision of our cosmic birth rooted in the quantum structure of reality itself. It offers a universe without a true beginning, but with a definite transition, a turn in the road hidden by quantum fog. It does not require an infinite multiverse or designer, but suggests that the laws of physics woven into the fabric of space contain their own recipe for renewal. It is a story still being written, waiting for the universe to reveal whether its deepest geometry is built from loops, and whether our greatest beginning was in fact a magnificent rebound. Perhaps the most honest answer to the cosmic riddle is also the most unsettling. After exploring 24 controversial theories, from quantum fluctuations to simulated realities, we must confront a final, overarching possibility. The ultimate origin of the universe may lie permanently beyond the reach of human comprehension. Our minds evolved to navigate a world of medium-sized objects moving at modest speeds, might simply be incapable of grasping the true nature of a reality without time, without space, and without cause. This is not a surrender, but a profound recognition of our own limits. Consider the very tools of our inquiry. We seek explanations through cause and effect, a chain of events stretching backward in time. But what if time itself, as we understand it, is an emergent property, a local phenomenon that only came into being with the Big Bang? Asking what came before the Big Bang might be as meaningless as asking what is north of the North Pole. The question presupposes a framework, a linear timeline that simply did not apply. Our language and logic are built for a universe that already exists, making them clumsy, perhaps useless for describing its absolute beginning. Philosophers label this the idea of a brute fact. Some things may not have an explanation, they simply are. The universe, with its specific laws and constants, might be one such brute fact. It is uncaused, unexplainable, and fundamental. This is not a satisfying answer to our yearning for a story, but it might be the most accurate one. The laws of physics as we know them break down at the singularity, and our current scientific paradigms, from general relativity to quantum mechanics, hit a wall. This suggests we are missing a deeper framework, a theory of quantum gravity that could reshape the question entirely. Embracing this ignorance is not a failure of science, it is its greatest engine. Every we don't know is a frontier. The mystery of the Big Bang singularity directly motivated the development of cosmic inflation and string theory. The fine-tuning problem forced us to consider the staggering vastness of the multiverse. Our confusion is a compass pointing toward the next revolution in understanding. To stand before the deepest mystery and admit we may never solve it is an act of intellectual courage. It places us in a proper relationship with the cosmos, not as masters destined to unravel every secret, but as curious participants in a reality far stranger than we can dream. This humble perspective does not end the quest, it liberates it. It allows us to explore every wild possibility, from holographic origins to cosmic natural selection, not as final truths, but as magnificent chapters in an ongoing story of human curiosity. The universe may keep its first secret forever, but in trying to uncover it, we discover something equally profound: the limitless capacity of the human mind to reach for the stars, even when the answers lie in the dark. So we stand at the edge of the known, surrounded by 24 maps of creation, each drawn from a different dream of reality. From the mathematical certainty of a cosmic bounce to the philosophical vertigo of a simulated existence, this journey reveals less about a definitive answer and more about the incredible spectrum of human thought. We have seen the universe imagined as a hologram, a quantum fluctuation, an eternal cycle, and a divine thought. The sheer diversity of these explanations is not a sign of confusion, but a testament to the power of the question itself. Our quest for a beginning is about more than physics or cosmology. It is a fundamental expression of the human spirit, a relentless drive to find our place in the story of everything. We are pattern seekers and meaning makers, and the greatest mystery of all ignites our deepest curiosity. Which of these visions feels most true to you? Does the elegant mathematics of a loop quantum bounce speak to a sense of natural order, or does the purposeful fine-tuning of the cosmos point toward something more intentional? Perhaps the infinite, branching multiverse captures the sheer scale of possibility, or the idea of a timeless, mathematical existence satisfies your search for an ultimate foundation. There is no single answer here, only a magnificent conversation stretching across science, philosophy, and imagination. We want to hear which controversial theory reshapes your view of reality. Share your favorite in the comments below and tell us why it captures your mind. If you love exploring these cosmic mysteries, subscribe and join us for more deep dives into the wonders of space, time, and existence. Wherever the truth may lie, never stop looking up at the stars with that same sense of wonder. Keep questioning, keep wondering, and keep reaching for the next horizon.